Hello, I'm John Cottrell from Matrix Science. This presentation deals with the scoring and statistics of database searching using Mascot. It isn't a highly mathematical treatment, more an attempt to give a clear description of the key concepts and the safeguards that we have against getting misleading results. This is the Mascot result report for a peptide mass fingerprint search. There is a list of proteins, each of which matches some of the experimental peptide masses, but the report tells us that these matches are not statistically significant. The score threshold for this search is 76, and the top scoring match which we've obtained is 47. The graph is a histogram of the scores of the top 10 matches, and as you can see, all of them are in the area shaded green, which is used to indicate random, meaningless chance matches. What exactly do I mean by probability-based scoring? We calculate, as accurately as possible, the probability that the observed match between the experimental data and mass values calculated from a candidate peptide or protein sequence is a random event. The real match, which is not a random event, then has a very low probability. We can then reject anything with a probability greater than a chosen threshold, maybe 1%. Why is probability-based scoring important? Well, in the case of a peptide mass fingerprint, how else would you judge whether a protein hit was meaningful? In the case of MSMS data, it's actually very difficult to judge whether a match is significant or not simply by looking at the spectrum. Let me illustrate with an example. This match between a peptide sequence and a spectrum has a good number of matches to both Y and B ions, highlighted in red. All of the major peaks above 200 Daltons look to be labelled. Could such a match have occurred by chance? Well, you can't tell, because you can match anything to anything if you're going to try hard enough. If this sounds strange, here's a simple analogy. If I say I was tossing a coin and got 10 heads in a row, does that mean there is something strange about the coin, like it has 2 heads? Well, you can't tell, because you also need to know how many times I tossed the coin in total. If I pick it up off the table, toss it 10 times, and put it back on the table, and I get 10 heads in a row, then yes, that would suggest it was not a fair coin. But if I tossed it 10,000 times, at some stage during that sequence, I would definitely expect to get 10 heads in a row, possibly more than once, possibly 11. So it isn't just a matter of whether you get 10 heads in a row, or how many Y or B ions you manage to match. It's a case of how hard did you try to find the match? How many trials did you make? In the case of database searching, this means how large was the database, what was the mass tolerance, how many variable modifications, etc., etc., etc. These are very difficult calculations to do in your head, but they're very easy numbers for the search engine to keep track of. Now, if we look at the expect value for this particular match, it's 1. That is, we could expect to get this match purely by chance. It looks good, but it's actually, for this particular search, just a random match. If I now show you a better match, then it is easy to dismiss the previous one as inferior. We can all make that judgment very easily. This match has an expectation value of less than 1 in 10,000. It's definitely not a random match. The challenge is, what if you don't have the better match to compare against? Maybe this sequence wasn't in the database. If you only had the inferior match, how would you decide by looking at it whether it was significant or not? The other interesting question, of course, is whether this is the correct match. Who can say that a better match isn't possible, where we get the last Y ion and some more of the B ions fall into line? If we use probability-based scoring, we can apply standard statistical tests of significance to the results. If we don't do this, then the only way to know the level of false positives is a target decoy search, and this isn't always possible. For example, if we're searching a very small number of spectra. Probability-based scoring calculates the probability that the match is random. That is, the probability that the match is meaningless or incorrect. People often ask, can we report the probability that the match is correct? Is this possible? Well, it's certainly possible if you're analyzing a known protein or a standard mixture of proteins. If you know what the sequences are, or you think you know, then the matches to the known sequences are defined to be correct, and those to any other sequences are defined to be wrong. If the sample is an unknown, then it's difficult even to define what we mean by the correct match. This is a typical MSMS search result, and we see a series of high-scoring homologous peptides matched to a particular spectrum. The sequences of the top 4 matches are very similar, and their expect values vary from random through to very unlikely to be random. The best match has an expect value of 2e to the minus 5. However, we cannot be sure that this is an identity match to the analyte peptide. It's simply the best match we could find in the database. There's always the possibility that a better match exists, but is not in the database. So, to call it definitively the correct match could be misleading. What really matters here is that we have a mechanism to discard matches that are nothing more than random or chance matches. It's a similar situation in BLAST, except that with BLAST you have the luxury of seeing when you have a perfect identity match. Here, the identity match has an expectation value of 1e to the minus 6, which reminds us that even this would be a random match if the database was 1,000,000 times larger. The match with one residue of error is not worthless, it's not incorrect, it has an expectation value of 1e to the minus 5 and is still a very good match. It just isn't quite as good a match as the one above. When we are doing probability-based matching, we're not scoring just the quality of the spectrum, we're scoring whether the match is random or not. So even when the mass spectrum is of very high quality, if the peptide is so short that it could occur in the database by chance, you can never get a very good score. The situation in BLAST is identical. Even though this is a perfect identity match, the expectation value is still high at 48. It's just a random match because of the size of the database. Hence, our earlier tip to discard spectra with low mass precursors, because searching them is basically a waste of time. For a peptide mass fingerprint, there's just one score that matters, the protein score. This tells us whether the match is significant or not, and is determined by calculating the probability of getting the observed number of peptide mass matches if the protein sequence was random. For an MSMS search, we have 2 scores. The important one is the peptide match score or iron score. This is the probability of getting the observed number of fragment iron matches if the peptide sequence was random. However, most people are interested in which proteins are present rather than which peptides have been found. So, we assign peptide matches to protein hits and provide protein scores for MSMS searches so that the proteins with lots of strong peptide matches come out at the top of the report. However, it's very important to understand that the protein score in an MSMS search is not statistically rigorous. It's simply a way of ranking the protein hits. This is why there is no expect value for the protein score in an MSMS search, and why there is a short explanation at the top of every report. Because a mascot score is a log probability, assigning a significance threshold is very simple. It's just a function of the number of trials, the number of times we test for a match. For a peptide mass fingerprint, it's simply the number of entries in the database. For an MSMS search, it's the number of peptides in the database that fit to the precursor mass tolerance, the number of peptide candidates. For an enzyme such as trypsin with a reasonable mass tolerance, this number will be less than the number of entries in the database. For a no-enzyme search, the number of trials will often be more than the number of entries in the database. So, for example, if we're comfortable with a 1 in 20 chance of a false positive match, and we're doing a peptide mass fingerprint search of a database that contains 500,000 entries, we're looking for a probability of less than 1 in 20 times 500,000, which corresponds to a mascot score of 70. If we could only tolerate a false positive rate of 1 in 200, then the threshold would rise to 80, 1 in 2000 it would be 90, etc., etc. For MSMS searches with trypsin and a reasonable mass tolerance, the numbers tend to be lower. The default identity threshold is typically a score of around 35 or 40. Unfortunately, MSMS spectra are often far from ideal and have poor signal-to-noise or gaps in the fragmentation. In such cases, it's often not possible to reach the identity threshold score, even though the best match in the database is a clear outlier from the distribution of random scores. To assist in identifying these outliers, we also report a second, lower threshold for MSMS searches, the so-called homology threshold. This simply says that the match is an outlier. But, in practice, from measuring actual false positive rates by searching large data sets against decoy databases, we find that the identity threshold is usually very conservative, and the homology threshold actually provides a number of additional true positive matches without exceeding the specified false positive rate. In addition to the score, we also display an expect or an expectation value. The expectation value does not contain new information. It can be derived directly from the score and the threshold. The advantage is that it tells you everything you need to know in a single number. It's the number of times you could expect to get this score or better by chance. A completely random match has an expectation value of 1 or more. The better the match, the smaller the expectation value. The most important attributes of a scoring scheme are sensitivity and specificity. That is, you want as many correct matches as possible and as few incorrect matches as possible. This is often illustrated in the form of a receiver operating characteristic, or ROC plot. This plots the relationship between the true positive and false positive rates as the threshold is varied. The origin is a very high threshold which lets nothing through. At the top right, we have a very low threshold which allows everything through. Neither is a very useful place to be. The diagonal represents a useless scoring algorithm that is equally likely to let through a false match as a true one. The red curve shows a useful scoring algorithm, and the more it pushes the curve up towards the top left-hand corner, the better. Setting a threshold towards this top left-hand corner gives a high ratio of correct matches to false matches. A few years ago, there was a little too much focus on sensitivity and not enough consideration given to specificity, so that some of the published lists of proteins were maybe not as accurate as the authors might have hoped. A growing awareness of this problem led to initiatives from various quarters, most notably the editors of Molecular and Cellular Proteomics, who held a workshop in 2005 to define a set of guidelines which have since been revised. For large-scale studies, there is a requirement to estimate the false discovery rate, and one of the most reliable ways to do this is with a so-called decoy database. This is a very simple but a very powerful technique. You repeat the search using identical search parameters against a database in which the sequences have been reversed or randomized. You don't expect to get any real matches from the decoy database, so the number of matches that are found is an excellent estimate of the number of false positives in the results from the target database. You've probably read a lot in the literature about whether the decoy sequences should be reversed or randomized, and whether to search a single database containing both target and decoy sequences or search separate databases. I suggest the most important thing is simply to do a decoy search, any type of decoy search. The important thing to know is whether your level of false positives is 1% or 10% or 100%. It really is less of a concern whether it's 1% or 1.1%. Now, although this is an excellent validation method for large datasets, it isn't useful when you only have a very small number of spectra, because the numbers are simply too small to give any kind of accurate estimate. Hence, this is not a substitute for a stable scoring scheme, but it's an excellent way of validating important results prior to publication. On our public website, there is a help page devoted to decoy database searches. It includes a download link to a utility program that allows you to create randomized or reverse databases. If you have an early version of Mascot, or if you want to verify the results from another search engine, you can use this utility to create a decoy database for your searches. Because more and more people wish to perform decoy searches routinely, we've also added this into Mascot as a built-in part of the search. If you choose the decoy checkbox on the search form, then every time a protein or peptide sequence from the target database is tested, a reversed or randomized sequence of the same length is automatically generated and tested in parallel. The average amino acid composition of the random sequences is the same as the average composition of the target database. The matches and scores for the decoy sequences are recorded separately in the result file so that you can generate a report of the decoy search should you so wish. The result of the automatic decoy search is equivalent to searching a separate database rather than searching a concatenated database. When the search is complete, the statistics for matches to the decoy sequences are reported in the result header. If you change the significance threshold, the numbers are recalculated. In Mascot 2.4 and later, there is a button to adjust the significance threshold automatically to achieve a chosen false discovery rate value. For example, if we choose 1% FDR using the homology threshold, the significance threshold has been automatically adjusted from 0.05 to approximately 0.01. Now, why do we get false positives? Do they reflect some defect in the search engine? Well, let's have a closer look. If you click the link here, then you will see the results from searching the randomized database. These results have been saved into new sections of the result file on the Mascot server. This means you can view these results in exactly the same way as if we had performed a separate search against a randomized database that we had created manually. We can see matches here with scores of 37 and 51, with expect values well below 1%. If we click on the query number link to display the peptide view for one of these matches, this is what it looks like. A pretty decent match from a decoy sequence. Triptych peptide, no variable mods, good run of B and Y ions, most of the larger peaks are matched. Now, asking whether this is correct or wrong becomes almost a philosophical question. The fact is, when we search very large numbers of spectra against very large sequence databases, we will see matches as good as this by chance. No amount of expert manual inspection can prevent this. Database matching is a statistical process, and for this search, the number and magnitude of the false positives is well within the predicted range, and this is all we can ask for. Sensitivity improvement is always going to be a hot topic. One of the limitations of database matching is that even the best scoring scheme cannot fully separate the correct and incorrect matches, as is shown here in a schematic way. The score distribution for the correct matches overlaps that of the incorrect matches, and when we use a decoy search, we are deciding where to put a threshold of some sort to separate the two distributions. But what if we could find a way to pull these two distributions further apart, to better resolve them? In other words, is there a way to improve the specificity of the scoring? One of the first attempts to do this was peptide profit from the Institute of Systems Biology. This was and is popular for transforming sequence scores into probabilities. It takes information about the matches in addition to the score and uses an algorithm called expectation maximization to learn what distinguishes correct from incorrect matches. Examples of the additional information might be precursor mass error, number of miscleavages, or the number of triptych termini. A more recent development has been to use the matches from the decoy database as negative examples for a machine learning classifier. Percolator trains a machine learning algorithm called a support vector machine to discriminate between a subset of the high-scoring matches from the target database, which we assume are correct, and the matches from the decoy database, which we assume are incorrect. This can give a very substantial improvement in sensitivity. The original Percolator was implemented mainly with Sequest in mind, but Marcus Broch at the Sanger Institute wrote a wrapper that allowed it to be used with mascot results and publish results such as this. The black trace is the sensitivity using the mascot homology threshold, and the red trace is the sensitivity after processing through Percolator. It doesn't work so well for every single dataset, but when it does work, the improvements can be most impressive. The developers of Percolator kindly agreed to let us distribute it and install Percolator as part of Mascot. This option is available for any search that has at least 100 MSMS spectra and auto-decoy results, but it works best when there are several thousand spectra. To switch to Percolator scores, just check the box in the result report and choose Filter. This is the example search that is linked from the MSMS Summary Report help page. Using the mascot homology threshold for a 1% false discovery rate, there are 1,837 peptide matches. Rescoring with Percolator gives a useful increase to 1,985 peptide matches. Note that in general, the scores displayed after switching to Percolator will be lower. The posterior error probability reported by Percolator is tabulated in the expect column. A mascot score is calculated from the expect value and a single fixed score threshold, which we describe as the identity threshold, with a value of 13, that is, minus 10 log of 0.05. By keeping the score, threshold, and expect value consistent, we hope to avoid breaking any third-party software that expects to find these values.